All right, welcome to this explainer. Today, we're going to completely demystify artificial intelligence. We're cutting straight through all the noise, dropping the Hollywood sci-fi fantasies, and looking squarely at the fascinating and sometimes pretty harsh mathematical reality of what AI actually is.
So let's just kick things off with a question that, might sound a little funny at first, but it actually gets right to the heart of the whole thing. Where on earth are our robot butlers? I mean, despite decades of intense, incredibly well-funded research, the highly intelligent, autonomous robotic assistants we were promised in countless books and movies simply do not exist. To understand why, we really have to look back at how this field was actually built from the ground up.
Here's our roadmap for today. 1. The grand AI dream. 2. Turing's electronic brains. 3. The Turing test trap. 4. The golden age. And 5. The complexity barrier.
To guide us through all this, we're drawing directly from Michael Wooldridge's totally brilliant book, A Brief History of Artificial Intelligence. He basically strips away all that media hype and walks us through the constant boom and bust cycles that have defined AI history, which is a crucial dose of reality for anyone trying to understand this tech today.
All right, let's jump right into section 1. The grand AI dream. Myths versus reality.
We really need to talk about this massive, yawning gap between what we deeply want AI to be and what it actually fundamentally is. On one hand, you've got this grand dream, the pop culture AI that's self-aware, conscious, and walking around our messy human world autonomously. But the harsh, practical reality? Computers are just machines. They blindly, faithfully follow explicit mathematical instructions. There's no magic spark in there. It's literally just an underlying recipe.
Moving right along to section 2, Turing's electronic brains.
So let's travel back to 1935 and meet the brilliant mathematician Alan Turing. He essentially invented the modern computer almost by accident while trying to solve this deeply complex mathematical puzzle. A computer is literally just a machine built to execute an algorithm. And an algorithm, that's just a precise list of instructions it follows by rote. So when those early newspapers were buzzing about electronic brains, it was super misleading. These machines do not think. They just follow instructions without a single ounce of actual, genuine intelligence. But, they do have one massive advantage over us: sheer, mind-blowing speed. To put this in perspective, a standard modern computer can execute up to 100 billion of these simple instructions every single second. Just think about that. If you sat down with a pencil and paper trying to manually do just 1 second's worth of a computer's work, doing one instruction every 10 seconds, no sleep, no breaks, it would literally take you 3,700 years. And that brings us to this really fascinating hierarchy of AI difficulty. The stuff we usually think of as requiring high intelligence, like, say, complex arithmetic, is actually incredibly easy to turn into simple recipes for a computer. We solved that decades ago. But the things we humans do effortlessly without even thinking, like perceiving a busy street corner so we can drive a car, brutally hard to write rules for. And things like writing a truly compelling story or interpreting a nuanced work of art, we still have absolutely no clear path to solving those. Which lead us perfectly into section 3, the Turing test trap, smoke and mirrors. As computers actually became a reality, people obviously started wondering, hey, how do we measure if a machine is truly acting intelligently? Turing proposed an imitation game. If a computer talks to a human through a screen and fools them into thinking it's human, boom, it passes. But here's the trap. This created a massive divide between strong AI, which genuinely understands what it's saying, and weak AI, which just fakes it. Because the test only cares about the final output, it totally incentivized researchers to use cheap behavioral tricks instead of building genuine comprehension. A perfect example of this smoke and mirrors tactic is Eliza, an MIT chatbot from the 1960s. It was designed to mimic a psychotherapist, and wow, it fooled users into pouring their hearts out to it. But Eliza understood exactly zero of it. It just scanned for keywords and blindly spat back canned phrases. If you asked it the meaning of life, it would literally just bounce your words right back at you with a generic script. Total parlor trick, not true intelligence. All right, next up, section 4, the golden age, spanning from 1956 to 1974. Despite those limitations, the field got its official name in 1956 at a Dartmouth summer school, sparking this era of just unbridled optimism where they genuinely believed human-level machine intelligence was right around the corner. And, they had reason to be excited. Take the Charlotte program. A user could type plain English commands, telling a virtual robot arm to pick up blocks and put them in boxes, and the system would flawlessly do it. But, and it's a big but, this was a blocks world. It was a perfectly closed, simulated virtual environment. It completely ignored the messy, totally unpredictable physics of the real world, where a robot might drop a block or a shadow might look like a solid edge. So at the core of these early successes was a fundamental AI problem-solving technique called search. It's basically a brute force method. You start at the beginning, mathematically map out every single possible move you can make, check if any of them win the game, and if not, you map out all the next possible moves from there. Sounds like a solid plan, right? It works perfectly, in theory.
But let's look at what happens when you actually map that out. Even for a super simple children's puzzle like the Towers of Hanoi, it instantly generates this massive, branching search tree just to map out the first few moves. Because the computer doesn't possess human intuition, it literally has to systematically build out this massive tree just to figure out what to do. And that tree grows astonishingly fast.
This brings us right to our final section, Section 5, the complexity barrier. Math hits hard. Remember that rapidly expanding search tree? Well, if you try to use that exact same brute force technique to play a slightly more complicated board game like Go, by the time the computer looks just 4 moves ahead, it has to evaluate 3.9 billion possible board states. 3.9 billion just 4 moves in. This mathematical nightmare actually has a name. It's called combinatorial explosion. It happens when a problem has successive choices that multiply the possible outcomes completely out of control. To put this terrifying math into perspective, a standard 200-move game of Go generates more possible board states than there are atoms in the known universe. I mean, wow. No computer, no matter how ridiculously powerful, is ever going to brute force its way through that. So once researchers realized they had slammed face-first into this immovable mathematical barrier, these are a class of problems known as NP-complete, by the way, the whole atmosphere shifted. That boundless optimism of 1956, it turned into immense frustration by 1972. The UK published the famous Lighthill report, directly calling out that AI had failed to overcome combinatorial explosion. Funding totally evaporated overnight. The golden age violently crashed into what we now call the AI winter.
And the scientific backlash from this failure was absolutely brutal. Critics were quick to point out all the wildly exaggerated promises. The philosopher Hubert Dreyfus even published a damning report analyzing the whole field, and he provocatively titled it Alchemy and AI. He was directly comparing these highly respected, optimistic scientists to medieval alchemists who foolishly believed they could magically turn lead into gold.
Which brings us to our final takeaway for this explainer. Today, we're riding yet another massive global wave of AI excitement and hype. And sure, the technology has absolutely evolved, but the fundamental nature of computing hasn't. So we're left with this really provocative question. As we push forward, will we remember the hard mathematical limits of the past? Or are we just chasing alchemy all over again? Remember, you're only human, and machines, well, for now at least, they're still just incredibly fast recipe followers. Thanks so much for joining me today, and keep questioning the hype.